So how you get to this higher level is missing in both in primary and secondary schools. So here we have the same situation. They have a set of computing methods that work, but only a limited level of understanding of what's going on. Well, then algebra, which was done by Irene van Stiphout, she chose some tasks that she knew would require some understanding. One of them is taken from Wenger, who talked about the global substitution principle, and it's a task that goes like a square root of b is 1 plus 2a square root of 1 plus b, and then write the formula for a. And if you look at it closely, it's a equation in A. You don't have to do anything with the square roots, but students see square roots, so they start trying to take the quadratics and get into a big mess. And you can see that in the results in grades 10, 11, and 12, hardly anybody gets the right answer. Something similar for a task like this multiplication, where you would expect that the students would say, well, I know if x minus 5 is 0, then it will be 0, the same for x plus 2 and so forth. Instead, they start working it out and run into problems. The students are familiar with similar situations where you have two factors, but three factors is new for them, and then it goes wrong. So then again, the same picture. They have rules for certain cases, but they have a limited level of computational, conceptual understanding. And in algebra, there is, if you look at textbooks, they do start with context, with understanding, but they quickly change to procedural approach. So the three studies basically show the same. And the focus is on routinizing strategies, procedures that work. And we call that, or as an explanation, we introduced the term task propensity, which we described as the inclination of teachers and textbook authors to think of instruction in terms of individual tasks that have to be mastered by the students. So this focus on individual tasks, and you have procedures that work for those tasks. That's what's happening. And of course, it's sort of natural also, because if you teach some students some things, you want them to practice. But the danger is that you're focusing on all those small things. And that relates, I think, to views on learning. And then we get back to this making connections I started with. Resek and Hall also claim that the popular view is similar to what's called the classic associative theory of learning, where knowledge consists of making connections, input, output connections, and things like that. And then testing is on whether these connections are made. Instruction is doing those connections over and over. And so the testing supports this tendency to look for this kind of teaching. And I should mention last, but if you look at curriculum documents, they also are written in terms of individual items. There may be some generalization, but always this have to be able to this, be able to do that, to that. So all these things come together and fostering this task propensity. Where, if you look at it from the community of mathematics education researchers, then you would expect there would be a link between a view on how mathematics learning proceeds and how you formulate your goals. And the general understanding is that constructing mathematics consists of a series of transitions from processes into objects. You start with counting, and it become numbers, and numbers you get into number relations, and so forth. Every time you construct new mathematical objects which you operate with, which allows you to create new objects which you operate with, and so forth. And many people just in the scientific world say that Schwarz, Stoll, Freudenthal, Debesky is a sort of general view. But then we argued, well, then the goals of mathematics education should be described in terms of mathematical objects and mathematical relations instead of testing items. So if we look at addition and subtraction, then they should have a sense of how decimal numbers are constructed, using units of 10 and reasoning with them, splitting numbers in tens and ones and so forth, expounding this to number relations where you have other combinations like 73 and 26, and then see the interconnectedness between addition and subtraction, where this picture could mean both various subtractions or additions. And what we would like to emphasize, instead of procedures, we want students to work with number relations. And the highest level here would be, a higher level would be, if students are thinking of a sum as an object. And then you can compare the sum 65 plus 17 with the sum 65 plus 7. And see that the first one is 10 more without doing the calculation. And I return that to show that this is something you need in algebra. For fractions, a similar story. You would like to start with seeing fractions as a junction in this network of number relations, like 3/4 is a quarter and a quarter and a quarter, or 3 times a quarter, or 1 minus a quarter, or a half and a quarter. So you develop all those number relations, which then can be used in a similar way as we did in the beginning with numbers up to 20. So again, returning to this idea of building a set of number relations, seeing numbers as objects and using these. And then of course, on a higher level, you want them to be aware that 3/4 is both a number and an indication for a process. I guess 3 divided by 4 instead of what's written there. And then you can reason about 16 times 3/4, because that means 16 times 3 divided by 4. And 3/4 of 16 is 3 divided by 4 times 16. And if you have a sense of how those operations hang together, so you have to be able to think on a higher level about operation, multiplication and division in relation to fractions, to be able to reason about this and to really understand the common rule of denominator and denominator and so forth. So, and then on a, again, higher level, students have to come to see a product as such, as an object you can reason with. And so you can go up and up again. And I give an example there which I skip. And this relates to what Arcavi calls structure sets and symbol sets, the way you can see relations in algebraic expressions, and with the idea of structural and procedural of Schwarz. And also interesting is here that you can shift between different ways of looking at the same object. So 2x plus 7 can be seen as a computational description. You have to do something. Or as an object you can reason with. For instance, if you have 2 plus x to the magnitude of 3, or if you make this comparison, which is similar to what I did earlier, 2x plus 17 is 10 more than 2x plus 7. This often is a problem for students because they only are familiar with the computational prescription, but they really need to be able to think of these things as objects. In summary, the students get a restricted set of computing methods and a limited level of understanding. We think focus on the individual tasks and the results is one of the key problems. The other one is that goals are not formulated in terms of higher level conceptual mathematical understanding, not in textbooks, nor in tests or curriculum documents. In addition, there's the problem with the inquiry classroom culture. This was already found in the study I mentioned from 1991. And the latter is a problem in which the Netherlands is not unique. I think the mathematics education community has been trying to get problem-centered inquiry math implemented or enacted for some decades now. And still we are struggling. But at the same time, we learned a few things, and I want to just go through them quickly. One of them is this whole idea of classroom culture or social norms, social mathematical norms, identified by Gravemeijr, but also by Rousseau. And one of them is the orientation of the students, task orientation, the need to cultivate mathematical interest, to frame topics for discussion. I just will work them out in the next slides, I guess. It's going to do what I wanted to do. I don't remember what magic trick we used last time. Maybe just go back and start again. Let me try that. There's no mouse to be seen. Oh, it's already. I don't know what you did, but okay. Okay. I start with social norms, and the point is here that students have different expectations of their role in, let's say, traditional classrooms than in inquiry classrooms. In a traditional school math classroom norms, students have to come to grips with the knowledge the teacher already has. The teacher's role is to explain and clarify. The student's role is to figure out what the teacher has in mind. It's quite different from inquiry classrooms, where the obligation of the student is to explain and justify his or her solution, try and understand what other people are saying, ask questions if they don't understand, and challenge arguments they don't agree with. And the teacher's obligation is to give tasks and ask questions, not to explain. And they also discuss social mathematical norms. What do we think mathematics is? What is our view on mathematics? And in inquiry classrooms, you want to see mathematics as, or issues there are, what counts as a mathematical problem? And what's as a solution? And what's a more sophisticated solution, so you can reason about these things. And to establish the new social norms, it's not just a matter of telling the students. The students have to experience that things are going different, that different things are appreciated. And the teacher can use instances to where something goes according to the norms, to say, well, this is what I want, or if it's not going according to the norms, explaining this is what I don't want. And the teacher can do a lot of things to cultivate an inquiry classroom culture. And I'll just skip this slide and start with a video where a teacher is doing all this. And the story is from Math in the City, a project by Martin Dolk and Cathy Vosno. And the problem is about how long to cook a turkey. The turkey is 24 pounds and it takes 50 minutes per pound. And this is a real problem, often in the US, where you always have to wait very long before the dinner is ready.